Hello everyone, welcome to GNANA DEEKSHA concept based digital learning. I am Krishnaveni working as JL Chemistry in TSWREIS Junior College, Mahendra Hills, Hyderabad. We all know that electrons are revolving around the nucleus, and is it possible to remove the electron? Yes, if we give some energy to the electron will be removed easily. And what is that amount of energy given to the element to remove the electron? That is called as ionization energy. So, in our today's lesson, we are going to learn about the outcomes of this ionization energy and the factors that influence the ionization energy and why IE2 is greater than IE1 and what are the periodic trends. Okay, let us see. What is ionization? Ionization is the removal of electron from the outer orbit. Before we start that ionization energy, let us recall the electronic configurations of first 36 elements, that is from hydrogen to krypton. Okay. Also, we can recall the electronic configuration in first three orbits. Okay. Now, what is ionization energy? It is the minimum amount of energy required to remove the electron from the valence shell of a neutral gaseous atom. And as we are removing the first electron, it is also called as first ionization energy. And the example is aluminium. When an electron is removed from the aluminium, it forms Al plus ion. And here the energy given is 580 kilojoules per mole. If we want to remove another electron from the same element, again we have to give energy, which is termed as second ionization energy. And it is defined as the amount of energy required to remove a second electron from the gaseous monopositive ion to form a dipositive ion is called second ionization energy. And here the second energy that is given is more than that of the first ionization energy, and the value is 1820 kilojoules per mole. Let us see. This is the energy comparison between hydrogen, helium and lithium. In hydrogen, the electron is present in the first orbit, and in first orbit, the electron is in the 1s orbital. Here there is no shielding. The electron is directly exposed to nuclear force. Therefore, the electron will be pulled towards the nucleus very hard. And in such case, the amount of energy to be given, it will be more. And the energy here required is around 1310 kilojoules per mole. When you move to helium, here the electron enters into the same orbital and the electrons get paired up. When the electrons are paired up, they are very strong. That means it is very stable. From helium, it will be very hard to remove the electron, so that it requires more energy when compared to the hydrogen. That amount of energy is 2370 kilojoules per mole. When you move from helium to lithium, then here the electron is entering into the outer shell, that is a new shell. Therefore, the distance between the electron and the nucleus is increasing. Therefore, it requires less energy when compared to the hydrogen and helium to remove the electron. And here the energy is equal to 519 kilojoules per mole. That means for helium, it has highest ionization energy. Okay. And what are the factors that influence the ionization energy? Generally, the ionization energy is affected by different factors such as nuclear force of attraction, half-filled and completely filled orbitals, the shielding effect or screening effect, the nature of the orbitals, the penetration extent of the orbitals, and also the atomic size. Let us see one by one. What are those factors that influence the ionization potential? First one, effective nuclear charge. If greater is the magnitude of the effective nuclear charge, higher will be the amount of energy to be given to remove the electron. That means, with the increase of the magnitude of the effective nuclear charge, the magnitude of the ionization energy also increases. The effective nuclear charge increases from left to right in a period, as the electrons are entering into the same orbital across a period. Therefore, the ionization energies will be in the increasing order from first element to the last element, which are present in the same period. Here we can take the example of third period. In third period, the elements are sodium, magnesium, aluminum, etc. Which element has more energy means the element which is present at the last, that is argon. If you take the second period, the elements which are present are starts with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Here, neon has highest ionization energy. Okay, what is our second factor? The second factor is atomic size. Atomic size is also defined as atomic radius. What is atomic size? It is nothing but the distance between the nucleus and the outermost orbit of a given element. When the distance is increased, when new shells are added to the element, obviously the size will be increased, and as the size is increasing, the atomic size increases as well as atomic radius also increases. Greater is the atomic size of the atom. More far is the outermost electron from the nucleus, and hence lesser will be the force of attraction exerted by the nucleus on the outermost shell electron. Thus, higher the value of atomic size or atomic radius of an atom, lower will be the ionization energy. If you see the energies that are present in first group, and the element which has smaller size will have more ionization energy, and the element with larger atomic size has less ionization energy. If you see the atomic sizes of the elements that are present in the first group, the element starts with lithium, sodium, potassium, rubidium, cesium and francium. In francium, the size is large, therefore it has less ionization energy, followed by cesium and then by rubidium, followed by potassium, sodium and then comes lithium. And next factor is principal quantum number. Principal quantum number, it is given by Niels Bohr and it is denoted by N. And from this quantum number, we know that as the N value increases, the size of the atom also increases. That means the number of orbits that are added also increases. Greater is the value of N. The valence shell electron of an atom is farther away from the nuclear force of attraction. Hence, lesser energy will be required to remove the electron from such orbit. Thus, we can define it, the magnitude of the principal quantum number is more, then the ionization energy gradually decreases. That means the N value increases means ionization energy decreases. They are reciprocal to each other. Okay, our next point is shielding effect. What is shielding effect? It is also called as screening effect. Shielding effect is a phenomena where the core electrons that are present in the inner shells, they protect the outer electron from the nuclear pull. That is, the electrons which are present in the inner shells, they are forming a screen-like structure which protect the electron that is revolving in the outer shell from the nucleus. That is, when the shielding effect is more, that means when the screening effect is increased, the lesser will be the nuclear pull on the electron. Therefore, it is the field of energy that requires to remove the electron from the outer orbit. And it is defined as the magnitude of the shielding effect increases with increase in the number of electrons in its inner shells, and also it depends on the shape of the orbital. The magnitude of shielding effect determines the magnitude of the force of attraction between the nucleus and the valence shell that is present in the outer orbit. Okay, greater is the magnitude of the shielding, the less energy will be required to remove the electron. That means when the shielding effect is increased, the ionization energy will be decreased and vice versa. And our next factor is half-filled and completely filled orbitals. According to Hund's rule, the elements which has half-filled configuration and completely filled configuration, they are said to be more stable. For example, the half-filled configurations are NS1, NP3 and ND5. Here, all the orbitals, when there are degenerate orbitals, each degenerate set of orbitals is filled with one electron. Because of one electron in all the orbitals, they experience stability, and this stability is called as half-filled stability. Whereas in the elements where the electrons present in different orbitals like S it is ns2, for P it is np6 and D for it is nd10. Then here all the orbitals are filled with electrons, that means all electrons are paired up, therefore they have very stable configuration. And in order to remove the electron from the elements which has half filled configuration or completely filled configuration, we have to give more energy. That means the relative energy that is required to remove the electrons from such elements or from the outermost orbit of such elements will be greater. For example, we take nitrogen and oxygen. In nitrogen, the atomic number is 7 and the configuration is 1s2, 2s2, 2p3. Here, p orbital has one unpaired electron in all the degenerate orbitals. That means in nitrogen, it is half-filled stability. Because of its half-filled stability, it requires more energy to remove the electron from the nitrogen. And whereas in case of oxygen, though it comes next to the nitrogen in a period, the oxygen has a lone pair of electrons and two unpaired electrons in the p orbit, and it will be easy to remove the electron from the oxygen when compared to removal of electron from the nitrogen. And the values of ionization energies for nitrogen and oxygen are, for nitrogen it is 1402.3 kilojoules per mole, whereas to remove the electron from the oxygen it requires only 1313.94 kilojoules per mole. That means greater will be the energy required to remove the electron from the half filled and completely filled configurations. Okay, these are the factors. Once we can recall again. What are those means? First one is atomic size, second one is nuclear force, and third one is shielding effect, fourth one is principal quantum number, fifth one is penetration of the orbitals. And let us see, why is second IE greater than first IE? When an electron is removed from its outer shell due to the less number of electrons in it, it forms a cation. In cation, the number of electrons is less than that the atom. Hence, the remaining electrons are pulled towards the nucleus more. The amount of energy required to remove another electron from the same orbit is increased successively. Therefore, the second ionization energy is always greater than the first ionization energy. Okay, if you take an example of sodium, if you take an example of magnesium, here in sodium, the electron that is present in the outer orbit is 1, that is the configuration is 1s2, 2s2, 2p6, 3s1. Only one electron is present in the outer shell and it will be easy for the sodium atom to remove the electron. Whereas in case of magnesium, the second electron is also entering into the same orbital. Therefore, it requires more energy when compared to the sodium atom. Like that, if you take the example of aluminium, atomic number of aluminium is 13 and outer shell it has 3 electrons, 2 electrons in s orbital and 1 electron in p orbital. If we want to remove all the electrons, we have different energies, which energies are called as successive energies or successive ionization energies. Due to the successive ionization energies, the aluminium can lose electron each at a time. And if we want to remove the first electron, the amount of energy given for first electron is called as first ionization energy, and the value here is around 577 kilojoules. And in order to remove the second electron from the Al plus ion, that is unipositive ion, the energy given is 1820 kilojoules per mole. And to remove the third electron, the energy given is called as third ionization energy, and that energy is equal to 2740 kilojoules per mole. If we want to remove one more electron from the aluminium, that is Al plus 3 ion, the amount of energy given is called as fourth ionization energy, and here the value is around 11,600 kilojoules per mole. At each successive energy level, the energy is increasing. From first ionization energy, it is increased to second, and likewise from second ionization and third to fourth. That means always the higher energy will be for last electron. That is why ionization energy IE2 is greater than first ionization energy IE1. Okay, let us take one example, sodium and aluminium. In sodium, if we want to remove the electron, we give less energy because here the electron is entering into the new orbit and there is less shielding. That means the electron is not attracted towards the nucleus more because of the larger atomic size here. Whereas in case of aluminium, as the electron is entering into the same orbit, it experiences more nuclear force when compared to the sodium atom. That is why it requires more energy than that of the sodium. And successive ionization energies are always greater than the previous ones because the electrons are being pulled away by more positive charge. That means the electrons will be pulled towards the nucleus with more energy. The effective nuclear force on the electrons will be more. That is why always the successive energies are greater. From this we can learn that IE2 is always greater than IE1. Okay, what are the properties? What are the trends of the ionization energy in a given period and group? In group, the energies are decreasing. In a group means they are vertical columns. In vertical columns, at each period, a new shell is added. That means, if you take an example of first group, lithium, sodium, potassium, rubidium, cesium and francium. In lithium, the second orbit is added. In sodium, the third orbit is added. Potassium, fourth orbit is added. Likewise, down the group, the number of shells that are added will be increasing. Therefore, when the shells are added, the size will be increased and the energy required to remove the electron will be easy for the elements with higher atomic number. That means down the group, ionization energy decreases. Okay, across a period from left to right. From left to right means the electrons are entering into the same orbit. That means if you take an example of third period, it starts with sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. The sodium, at sodium, a new shell is added and with increase in the atomic number, the electrons are entering into the same orbit. That means in sodium, the third orbit is added and for magnesium up to argon, the electrons are entering into the same orbit. Therefore, the energy increases from sodium to argon. And here we come across with again half-filled and completely filled configurations. The element with half-filled configuration, that is phosphorus with atomic number 15, it has more ionization energy when compared to the sulfur. In the same manner, argon has more ionization energy. That means the elements with half-filled and completely filled configurations across a period require more energy to remove the electrons. Let us see how these varies, madam. A successive ionization energies of some elements. If you take an example of calcium, here in calcium the atomic number is 20 and it has electrons in 4 orbits. That is, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. In order to remove electron each at a time, it has different energies and it requires more energy whenever we come across with the completely filled configurations, just like neon and just like argon, which is highlighted in pink color. Madam, next. Okay, and let us see. Ionization energy generally increases from left to right in a period because of the increase in nuclear charge and decrease in the atomic radius. And ionization energies generally decrease down a group due to the shielding effect and increase in the atomic size. Departures from these trends can usually be traced to repulsion between the nucleus and the electrons, particularly when electrons are occupying the same orbitals. It requires more energy to remove electrons from a successive series of energies where we come across with the aluminium in in our lesson. Okay, when all the valence electrons have been removed, the ionization energy take a quantum leap. That means there is a change in the energy levels. Okay, if you take the example of second group, it is just like similar to the first group. In first group, the element starts with lithium and ends with francium, which is a radioactive element, and its second group, it starts with beryllium, ends with radium. Here also, down the group, the atomic size will be increased, therefore ionization energy decreases. But the ionization energy of the second group elements is more when compared to the ionization energies of the first group elements because of the more nuclear pull towards the electrons with increase in the positive charge. Next, across a period, how the ionization energies will be changing. It is given in a graphical representation. You can see it. Here, the principal quantum number n value is increasing. If n is equal to 1, if n is equal to 2, how many elements are present? For n is equal to 1, we have two elements that are hydrogen and helium. In hydrogen, there is only one electron, and that electron is pulled by the nucleus with more effective charge. Therefore, it requires more energy to remove the electron. And here the energy is equal to around 1313 kilojoules per mole. And the second element present in n is equal to 1 orbit is helium. And helium, the electrons present are in the same orbit. Therefore, here the nuclear pull when compared to hydrogen is more. Therefore, it requires more energy. And the amount of energy required to remove the electron here will be around 2370 kilojoules per mole. And in next orbit, that is n is equal to 1, principal quantum number n is equal to 2, the elements that are present is 8, starts with lithium, followed by beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And basing on the number of electrons that are entering into the same orbit, the ionization energies gradually increases from lithium to the neon, and in between nitrogen, which has half-filled stability, the amount of energy required to remove the electron is more. Similarly, in n is equal to 3, that is principal quantum number value n is equal to 3, the number of elements present are again 8, starts with sodium, followed by magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. And here the same as the energy, as the number of electrons that are increasing, with increase in the atomic number, the ionization energy gradually increases from sodium up to argon. Okay, in n is equal to 4, likewise it starts with potassium. The same. Okay, when you compare the ionization energies of helium, neon, argon, krypton, etc., because of the smaller size of the helium, it has highest ionization energy among the periodic table. It has very small size and it consists of only 2 electrons, and that too the electrons are present in the first orbit. As the electrons are very close to the nucleus, here the nuclear pull is very high. Therefore, it has highest ionization energy. Okay, next one is lithium. From helium to lithium, there is a substantial drop in the ionization energy. Why? Because from helium to lithium, when we shift to lithium, a new shell is added. That means the distance between the nucleus and the outer shell is increased. Therefore, there is a change in the ionization energy. That means there is a drop in the value of ionization energy from helium to lithium. And when we move to beryllium, here again the energy is increased with increase in the atomic number. Moreover, here the electrons are paired electrons. That means the electrons which are present in second orbit for beryllium, they are paired. Therefore, the ionization will be increased gradually from lithium to beryllium. And from beryllium, when we move to boron, the energy further increases. Okay. And next comes carbon. And in carbon, the ionization energy gradually increases with increase in the atomic number from boron. And next comes nitrogen. And here there is a change in the order of ionization energies of nitrogen and oxygen. In oxygen, it has less energy. Why? Because it will be easy to remove the electron from the oxygen when compared to the removal of electron from the nitrogen because of its half-filled stability. Okay, next comes fluorine. Fluorine, already 7 electrons are there and it requires 1 more electron to complete its octet. Therefore, it is very hard to remove the electron from fluorine also. Therefore, gradually the energy increases. Next comes neon. Here the electronic configuration is 1s2, 2s2, 2p6. Here the outer shell is completely filled. It has octet stability. The element with octet configuration is very stable. Therefore, it requires more energy to remove the electron from the outer shell. And when you compare the energy of helium to neon, because of the larger size of the neon, it requires less energy to remove the electron, though it has octet configuration when compared to the helium. Next, sodium. In sodium, again a new shell is added. Therefore, there is a drop in the ionization energy from neon to the sodium. Because of its larger size, it requires less amount of energy to remove the electron from the outer shell. When you go to magnesium again, the amount of energy required to remove the electron will be increased. Like this, different energies are utilized, different energies are given to remove the electrons basing on their electronic configurations. Okay, and how these are changing in a period and group means, as we go down from top to bottom in a group, the ionization energies gradually decreases. When you move across a period from left to right, the ionization value increases with effective atomic number. That means with increase in the atomic number, the amount of energy required to remove the electron also increases, and it is explained clearly in the picture. Okay, next one is the trends of ionization energies. Next, we can see the elements that belongs to the S block and P block. S block elements, they are extreme left in the periodic table, and P block elements, they are at the right of the periodic table. The elements in the lower left of the periodic table tend to have lower ionization energy than those in the upper right. In the same manner, the elements that are present here is extreme left is S block elements and extreme right is P block elements. Moreover, the ionization energies are high at extreme top and right. That means the element which is having smaller size and which is present at the top of the right side, that is helium. Therefore, the element with highest ionization energy in the periodic table is helium. And down the group from helium, with increase in the atomic number, the new shells are added. Therefore, the ionization energy gradually decreases from helium towards the remaining elements. Okay, this is ionization energy. And what are the factors that influence the ionization energy? Let us do some questions here. Which has the higher value, the third ionization of aluminium or the third ionization energy of magnesium? Can you say? Yes, let us see. The third ionization energy of aluminium involves the following changes. Here, it will be very hard to remove the electron from the aluminium. We know it. But when come to the magnesium, after removal of 2 electrons, in order to remove electron means we have to remove the electron from the octet configuration. Therefore, it requires more energy. Despite magnesium having 12 protons in its nucleus and aluminium having 13, more energy is required to remove the third electron from magnesium. This is because the electron having removed is coming from an orbital shielding. Therefore, magnesium requires more energy to remove the third electron when compared to the aluminium. Okay, and one more question, let us see. Which has the higher value, the first ionization energy of sodium or the second ionization energy of magnesium? It is the second ionization energy of magnesium. Why? Because the first ionization energy of sodium involves only one step. That means when the electron is removed, it will be from the outer shell only. Once the electron is lost, it gains the stability. And in magnesium, 2 electrons are present in the outer shell. Therefore, after removal of first electron, the nuclear fuel will be more on the remaining electrons. Therefore, it requires more energy to remove the electron from the magnesium when compared to the sodium. However, magnesium has 12 protons in its nucleus, whereas sodium has only 11. The greater nuclear charge means the electron being removed is held more strongly and more amount of energy is required for magnesium. Okay, I will give one assignment. Just you memorize the ionization energies, series of ionization energies or successive ionization energies for the elements which are present in the third period, that is sodium, magnesium up to argon. Just you memorize. We can discuss in our next class. Thank you very much.